Tonight, we're going to explore one of the strangest contradictions in all of science. Because the universe, by every measure we have, should be full of life. The universe is almost 14 billion years old. It is filled with hundreds of billions of galaxies, each one containing hundreds of billions of stars, and around those stars, more planets than we can count. Many of those planets sit in exactly the right conditions for water to exist, for chemistry, and for life to begin. And yet, when we look out into that vast ocean of possibility, we hear nothing. No signals, no trace of anyone else out there. Just silence, stretching in every direction, as far as our instruments can reach. The numbers say we shouldn't be alone. And yet, here we are. By the end of tonight, you're going to understand why the numbers say life should be everywhere, why we found nothing despite decades of searching, and what that silence might actually be telling us about our place in the cosmos. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Start with the scale of what we're dealing with. Our galaxy, the Milky Way, contains somewhere between 100 billion and 400 billion stars. That number alone is hard to hold in your head, so let's break it down slightly. If you tried to count every star in the Milky Way, one number per second, without stopping to eat or sleep, it would take you more than 3,000 years just to finish counting. To put the scale of a single galaxy into perspective, our Sun sits roughly 26,000 light-years from the center of the Milky Way. Orbiting that center once every 225 to 250 million years, a single galactic year, meaning the solar system has completed only about 20 of these orbits since it first formed. And the Milky Way is only one galaxy. Current estimates suggest there are somewhere around 2 trillion galaxies in the observable universe, each one containing anywhere from a few million to several trillion stars of their own. Multiply those numbers together, and you get a figure so large it stops feeling like a number and starts feeling like an abstraction. Even our closest cosmic neighbors illustrate just how much room the universe has for hosting planets. The Andromeda Galaxy, our nearest large galactic neighbor, sits roughly 2.5 million light-years away. It contains roughly 1 trillion stars of its own, nearly 3 times as many as the Milky Way. It is currently on a slow collision course with our galaxy, expected to merge with it in roughly 4.5 billion years, long after our own Sun has already reached the end of its life, somewhere around 1 septillion stars. That's a 1 followed by 24 zeros. Light from the most distant galaxies we can observe has been traveling toward us for more than 13 billion years, meaning we're not just looking outward across space, we're looking backward across almost the entire history of time itself, all the way back to when the universe was still young, still assembling its very first generations of stars. The observable universe stretches roughly 93 billion light-years across, and that's only the portion we can actually see, limited by the fact that light itself takes time to travel, and the universe has only existed for about 13.8 billion years. Beyond that boundary, the universe almost certainly continues, possibly without end. It's filled with more galaxies, more stars, more planets, forever beyond our ability to observe, simply because their light hasn't had time to reach us yet. Now, attach planets to those stars. Thanks to missions like Kepler and TESS, we now know that planets are not rare. They're the rule, not the exception. Nearly every star we've studied in detail turns out to have at least one planet orbiting it. Some have 5. Some have 7, like the TRAPPIST-1 system, where 7 rocky worlds orbit a small red star just 40 light-years from Earth. Extrapolate that pattern across the galaxy, and you arrive at an estimate of roughly 100 billion planets in the Milky Way alone. Some of those are gas giants, uninhabitable by any definition we understand. But a meaningful fraction, based on the data we've collected so far, are small, rocky, and sitting in what astronomers call the habitable zone. The region around a star where temperatures allow liquid water to exist on a planet's surface, not too close, where the heat boils away every drop, not too far, where everything freezes solid. A narrow band of orbital real estate where the physics of water, the most important solvent we know of for chemistry, works in favor of life. The exact boundaries of a habitable zone depend heavily on the type of star involved. A hotter, brighter star pushes that livable band further outward, while a smaller, dimmer star pulls it in much closer. The calculation also depends on a planet's atmosphere, since a thick, insulating atmosphere can keep water liquid slightly outside the boundaries that a bare, airless world would require. Based on current estimates, there could be as many as 6 billion Earth-sized planets sitting in the habitable zones of sun-like stars in our galaxy alone. Location within the galaxy itself matters too. An idea astronomers call the galactic habitable zone. The center of the Milky Way, while dense with stars, is also an extremely hostile environment. It's home to Sagittarius A, the supermassive black hole anchoring our galaxy, surrounded by intense radiation, frequent supernova explosions, and gravitational interactions between closely packed stars. Any of these could sterilize a nearby planet or fling it out of a stable orbit entirely. The outer edges of the galaxy, by contrast, tend to have fewer heavy elements available, since those elements are forged inside stars and scattered through supernova explosions, processes that have occurred more frequently in the more crowded, element-rich inner regions of the galaxy over billions of years. Without enough heavy elements like carbon, oxygen, and iron, rocky planets may struggle to form at all, leaving outer regions of the galaxy dominated by simpler gas giants rather than Earth-like worlds. Our own solar system sits in a relatively quiet, unremarkable region, roughly halfway out from the galactic center, in what's sometimes called the galactic suburbs. It's far enough from the chaotic, radiation-soaked core to avoid its worst dangers, while still close enough to have access to the heavier elements needed to build a rocky planet in the first place. Some astronomers estimate that only a relatively narrow ring-shaped region of the galaxy offers the right balance of safety and raw material to reliably support the long-term stability that complex life appears to require. That region sits at just the right distance from the crowded, dangerous core, further narrowing the pool of truly promising candidate worlds, even among the billions already sitting in their star's individual habitable zones. 6 billion chances in just one galaxy for the right temperature, the right chemistry, the right conditions. And that's before you even start counting the other 2 trillion galaxies sitting beyond our own. This is where the math becomes almost uncomfortable. If life requires nothing more exotic than water, carbon, and a stable orbit, then the raw number of opportunities for it to appear somewhere in the universe is staggering beyond comprehension. Even if the odds of life beginning on any single world were absurdly low, 1 in a billion, 1 in a trillion, the sheer volume of planets should still produce life somewhere, probably in many places, possibly in a majority of galaxies. That's the heart of the paradox. Not that life is impossible, The numbers say the opposite. They say life should be common. They say intelligence should have emerged more than once, in more than one place. At some point across the 14 billion years, the universe has existed. And yet, we've found nothing. Not a single confirmed microbe beyond Earth. Not a single radio signal we can confidently attribute to another civilization. Not a single structure, probe, or artifact suggesting anyone else has ever looked back at us. We are, as far as the evidence currently shows, completely alone. That gap between what the numbers predict and what we actually observe is the puzzle we're going to spend the rest of tonight taking apart, piece by piece. It's worth remembering just how recently we confirmed any of this. For most of human history, the question of whether other stars had planets at all was pure speculation, debated by philosophers and dismissed by most scientists as unanswerable. That changed in 1995, when two Swiss astronomers, Michel Mayor and Didier Queloz, announced the discovery of a planet orbiting a sun-like star called 51 Pegasi, roughly 50 light-years from Earth. It was the first confirmed planet found orbiting a star like our own, and it immediately overturned expectations, since it turned out to be a gas giant roughly half the mass of Jupiter, orbiting so close to its star that a full year there lasts just over 4 days. Nobody had predicted a planet like that could exist, and its discovery forced astronomers to rethink everything they assumed about how planetary systems form. That discovery earned Mayor and Queloz the Nobel Prize in Physics in 2019, and it opened the floodgates. Within a few years, dozens of new exoplanets were confirmed, then hundreds. The real turning point came in 2009, when NASA launched the Kepler Space Telescope, a mission built for one purpose: staring continuously at a single patch of sky containing more than 150,000 stars, watching for the tiny, repeating dips in brightness that occur when a planet passes directly in front of its star. Kepler operated for 9 years, and by the time its mission ended, it had confirmed more than 2,600 exoplanets on its own, and contributed data leading to the confirmation of thousands more. The mission nearly ended early, in 2013, when a second of its 4 reaction wheels, the devices that kept the telescope precisely pointed at its target field of stars, failed, leaving it unable to maintain the stability needed for its original survey. Rather than abandoning the spacecraft, engineers devised an ingenious workaround using the gentle, consistent pressure of sunlight itself, along with its 2 remaining reaction wheels, to help stabilize the telescope. That allowed it to continue observing in a new, modified mission that astronomers named K2. The K2 mission went on to discover hundreds of additional exoplanets before the spacecraft finally ran out of fuel entirely in 2018. It revealed that small rocky planets, similar in size to Earth, are not rare oddities. They're common, found orbiting a huge fraction of the stars, Kepler observed. Its successor, the Transiting Exoplanet Survey satellite, known as TESS, launched in 2018, expanded the search to nearly the entire sky rather than a single patch, and has continued adding to the catalogue every year since. As of the most recent counts, astronomers have confirmed more than 6,000 exoplanets, with thousands more candidates awaiting confirmation. And that number represents only the planets we've managed to detect using our current, still fairly limited methods, which favor large planets orbiting close to their stars, precisely the kind that are easiest to spot. Smaller, more distant, more Earth-like worlds are far harder to detect, meaning the true number of planets in our galaxy is almost certainly far higher than what's currently catalogued. Some of the discoveries have been remarkable in their own right. The TRAPPIST-1 system, discovered in 2017, contains 7 roughly Earth-sized rocky planets orbiting a small, cool red dwarf star, with as many as 3 of them sitting within the star's habitable zone simultaneously. The system is remarkably compact, with all 7 planets orbiting closer to their star than Mercury orbits our Sun. Orbital periods range from just over 1 day for the innermost planet to less than 20 days for the outermost. An observer standing on one of these worlds could potentially see the neighboring planets as large, clearly visible disks in their sky, far larger than the Moon appears from Earth. Proxima Centauri b, discovered in 2016, orbits the closest star to our own Sun, just over 4 light-years away, and sits directly within its star's habitable zone. Though the star's frequent, violent flares raise serious questions about whether its atmosphere could survive intact. Proxima Centauri itself is a small, cool red dwarf, and the planet orbits it at a distance of roughly 4,600,000 miles, far closer than Mercury orbits our Sun, completing a full orbit in just over 11 days. Because it sits so close to its star, Proxima Centauri b is very likely tidally locked. One side permanently faces the star in perpetual daylight, while the other remains in perpetual darkness. That configuration creates extreme temperature differences between the 2 hemispheres and raises further questions about whether any atmosphere could circulate evenly enough to prevent gases from simply freezing out entirely on the planet's permanent night side. Despite these challenges, its sheer proximity, closer to Earth than any other known potentially habitable exoplanet, makes it one of the most intensely studied worlds beyond our solar system, and a leading candidate for any future generation ship or advanced propulsion concept that might one day attempt an actual interstellar journey. Every one of these discoveries adds another small piece of evidence to the same overall picture. A galaxy absolutely packed with planets, many of them sitting in conditions that, at least in principle, could support liquid water and the chemistry of life. Let's start with the ingredients. Because if you want to understand why scientists expected the universe to be full of life, you need to understand just how common the building blocks of biology actually are. For most of human history, people assumed that the chemistry of life, carbon, water, amino acids, the molecular machinery that makes a living cell function, was something special, something tied uniquely to Earth. That assumption has collapsed completely over the past several decades. Carbon, it turns out, is one of the most abundant elements in the universe, forged inside the cores of dying stars and scattered across space every time one explodes. Water is even more common. Astronomers have detected water ice on comets, on moons, on asteroids, drifting freely in interstellar clouds, and even inside massive quasars billions of light-years away, where a single reservoir of water vapor has been measured at roughly 140 trillion times the mass of all the water in Earth's oceans combined. Water is not rare. It might be one of the most common compounds in the entire universe. Then there are amino acids, the building blocks of proteins, the molecules that do the actual work inside every living cell. For a long time, scientists assumed these had to be manufactured by living organisms. Then, in 1969, a meteorite fell near the town of Murchison in Australia. When researchers analyzed it, they found more than 70 different amino acids embedded in the rock, several of which don't even appear in life on Earth. That meteorite had never been near a living thing. It formed in the early solar system, roughly 4.5 billion years ago, drifting through space long before life existed anywhere we know of. And it was carrying the chemical building blocks of biology inside it. Since then, similar discoveries have piled up. In 2016, the European Space Agency's Rosetta spacecraft detected the amino acid glycine directly in the thin cloud of gas and dust surrounding a comet called 67P, roughly 2.5 miles across, after spending more than 2 years orbiting it. Alongside the glycine, the spacecraft also found phosphorus, another element essential to life as we know it, forming the backbone of both DNA and cell membranes. This was the clearest confirmation yet that comets themselves, icy leftovers from the very formation of the solar system, carry the chemical building blocks of life within them. Not just meteorites that happen to fall to Earth, but the ancient, unaltered material still drifting through space today. Sugars have been found in meteorites. Nucleobases, the molecular letters that make up DNA and RNA, have been detected both in meteorites and in interstellar gas clouds thousands of light years from Earth. The chemistry of life, it turns out, doesn't need a planet to get started. It happens naturally, spontaneously, in the freezing vacuum of space, wherever the right raw materials and a bit of radiation happen to come together. This changes the entire picture. This raises another intriguing possibility, an idea called panspermia, the notion that life, or at least the ingredients for life, might not need to originate independently on every single world. Instead, it could be transported between planets, or even between star systems, hitching a ride on asteroids, comets, or dust ejected during violent impacts. We already know this kind of transport is physically possible. Scientists have found meteorites on Earth that originated on Mars, blasted off the Martian surface by ancient asteroid impacts, drifted through space for millions of years, and eventually landed here. If simple microbial life or resilient spores capable of surviving the vacuum of space existed on early Mars, it's not impossible that some of it could have made the journey to Earth inside one of those rocks, or that life could have traveled in the opposite direction. Some researchers have gone even further, proposing a concept called directed panspermia, the idea that an advanced civilization might deliberately seed lifeless planets with basic organisms, either as an experiment or as a way of spreading their own biological legacy across the galaxy. This remains firmly speculative, without direct evidence, but it illustrates another way the ingredients for life, and possibly life itself, could spread far beyond the single world where it first appeared, further increasing the number of places biology could theoretically take hold. It means every young solar system, every cloud of gas and dust that collapses to form a new star and its planets, is likely seeded from the very beginning, with the molecular ingredients biology needs. Life isn't waiting for a miracle. It's waiting for an opportunity. And on Earth, we've learned that once the opportunity arrives, life doesn't seem to need particularly gentle conditions to take hold. Consider the organisms called extremophiles, microbes discovered thriving in the most punishing environments our planet has to offer. There are bacteria living inside nuclear reactor cooling systems, absorbing radiation levels that would be instantly lethal to a human being. There are microbes found more than 2 miles beneath the surface of South Africa, in gold mines so deep and so hot that temperatures regularly exceed 60 degrees Celsius, or roughly 140 degrees Fahrenheit, surviving entirely without sunlight, drawing energy instead from chemical reactions in the surrounding rock. There are organisms living in the Atacama Desert, one of the driest places on Earth, in soil so dry it hasn't seen meaningful rainfall in centuries. There are creatures called tardigrades, microscopic animals barely half a millimeter long that can survive being frozen to nearly absolute zero, boiled past the point where water turns to steam, exposed directly to the vacuum of space, and bombarded with radiation thousands of times higher than what would end a human life. They simply power down, wait out the hostile conditions, and reactivate once things improve. This process, sometimes called cryptobiosis, involves the tardigrade expelling nearly all the water from its cells and replacing it with a protective, glass-like substance made from specialized proteins that effectively suspends its own metabolism to a rate so slow it becomes almost undetectable, a state it can remain in for years or even decades, before rehydrating and resuming normal life as though no time had passed at all. In 2007, European researchers even sent a sample of tardigrades into orbit aboard a spacecraft, exposing them directly to the vacuum of space and unfiltered solar radiation for 10 full days. The vast majority survived, and many went on to reproduce normally once returned to Earth, making tardigrades the first known animal confirmed to survive direct, unprotected exposure to outer space. Life on Earth, in other words, is not fragile. It is astonishingly persistent, capable of exploiting nearly any energy source, any temperature range, any chemical environment that offers even the smallest foothold. And this raises an obvious question. If life can take root in boiling acid, in solid ice, in the crushing dark miles beneath solid rock, why would we assume it needs anything close to Earth, like conditions, to get started somewhere else? The habitable zone, the narrow band where liquid water can exist on a planet's surface, might not even be the whole story. There are microbes called Deinococcus radiodurans, nicknamed Conan the bacterium by researchers, capable of surviving radiation doses roughly 3,000 times higher than what would end a human life, repairing its own shattered DNA within hours. Through a repair mechanism scientists still don't fully understand. There are organisms living inside solid rock, more than a mile below the ocean floor, discovered by drilling expeditions that pulled up samples containing living cells that had likely been metabolizing at an almost imperceptibly slow pace for possibly millions of years. Cut off entirely from sunlight, surface chemistry, or any of the processes we typically associate with a living ecosystem. There are bacteria found frozen inside ice cores in Antarctica, more than 2 miles beneath the surface, in lakes that have been sealed off from sunlight and the outside atmosphere for possibly millions of years. And when researchers finally drilled down and sampled that water directly, they found it wasn't sterile. It was full of life, adapted entirely to permanent darkness, crushing pressure, and near-freezing temperatures. None of these organisms are simple accidents. They represent entire branches of the tree of life that have specialized over countless generations in exploiting environments that would be instantly lethal to almost anything else on the planet. And this pattern, life persisting stubbornly in conditions once assumed to be impossible, keeps repeating every time scientists look somewhere new. Every one of these discoveries chips away at the old assumption that life needs gentle, Earth-like conditions to survive. If life on our own planet can be found in nuclear reactor cooling pools, in solid rock a mile underground, in ice-sealed lakes untouched by sunlight for millions of years, then the definition of a habitable environment starts to look far broader than anyone assumed, even 30 years ago. We now know that Jupiter's moon Europa likely holds a saltwater ocean beneath its icy shell, kept liquid not by sunlight, but by the gravitational flexing of Jupiter's immense tidal forces. Saturn's moon Enceladus does something similar, venting plumes of water vapor and organic molecules directly into space through cracks in its icy surface. Plumes that spacecraft have already flown through and sampled. The Cassini spacecraft, which orbited Saturn for 13 years before deliberately plunging into the planet's atmosphere in 2017 to avoid any risk of contaminating its moons, flew directly through one of these plumes in 2015, at an altitude of just 30 miles above the moon's surface. The data it collected revealed hydrogen gas venting from the moon's subsurface ocean, a strong indicator of hydrothermal activity occurring on the ocean floor, similar to the vent systems on Earth that host thriving ecosystems entirely independent of sunlight, drawing their energy instead from chemical reactions between hot water and surrounding rock. If hydrothermal vents exist on the floor of Enceladus's hidden ocean, and the evidence increasingly suggests they do, then this small, icy moon, barely 300 miles across, orbiting far from the warmth of the sun, may possess one of the more promising environments for simple life anywhere in our solar system. If oceans like these exist beneath the ice of moons in our own solar system, hidden from any telescope, warmed not by starlight but by gravity itself, then the number of potentially habitable environments in the universe multiplies far beyond anything the original habitable zone calculations accounted for. It's also worth asking whether life needs to resemble Earth's version of biology at all. Every example of life we know of relies on carbon as its structural backbone and water as its solvent. And there are good chemical reasons for that preference. Since carbon forms exceptionally stable and versatile molecular bonds, and water remains liquid across a wide, useful range of temperatures while dissolving a huge variety of chemical compounds. But some scientists have proposed alternatives. Saturn's largest moon, Titan, has lakes and rivers of liquid methane and ethane on its surface, existing at temperatures far too cold for liquid water, roughly -179 degrees Celsius, or about -290 degrees Fahrenheit. Some researchers have speculated that if life could ever arise using methane as a solvent instead of water, relying on different chemical reactions entirely, Titan might be one of the few places in our own solar system where such an alternative form of biology could theoretically exist. No evidence of this has been found, and many scientists remain skeptical that methane-based chemistry could support anything as complex as even the simplest form of life, given how much more sluggish chemical reactions become at such extremely low temperatures. Silicon has also been proposed as a possible alternative to carbon, since it sits directly below carbon on the periodic table and can form some similar types of chemical bonds. But silicon-based molecules tend to be far less stable and less versatile than their carbon-based equivalents, and no natural process we've observed anywhere produces the kind of complex, self-replicating silicon chemistry that life would require. For now, carbon and water remain by far our best working assumption, not because scientists have ruled out alternatives entirely, but because it's the only version of biology we've ever actually confirmed exists. And searching for what we understand remains far more productive than searching for what we can only theorize about. Every rocky planet with a molten core, every icy moon orbiting close enough to a gas giant to be squeezed and stretched by tidal forces, every subsurface aquifer, every buried ocean, every pocket of liquid water hidden from starlight but warmed from within. All of these become candidates. And when you add them to the 6 billion Earth-like planets already estimated to sit in the habitable zones of our galaxy's stars, the total number of places where life could plausibly exist becomes almost impossible to calculate. To make sense of just how many chances the universe has actually had, scientists often turn to a tool called the Drake equation, first proposed by the astronomer Frank Drake in 1961, ahead of a small meeting of researchers gathered to discuss the search for extraterrestrial intelligence. The equation isn't meant to give a precise answer. It's a framework, a way of breaking an impossibly large question down into smaller, more manageable pieces, each one representing a factor that multiplies against the others. The first factor is the rate of star formation in our galaxy, roughly 1 to 3 new stars forming every year. The second factor is the fraction of those stars that host planets, a number we now know, thanks to Kepler and TESS, is close to 1, meaning nearly every star has at least one planet. The third factor is the average number of planets per star that could potentially support life based on their size, composition, and position relative to their star's habitable zone. The fourth factor is the fraction of those potentially habitable planets where life actually begins. This is where the equation starts to run into real uncertainty, because we have exactly one confirmed example, Earth, and a single data point makes it almost impossible to calculate a reliable statistical average. The fifth factor is the fraction of life bearing planets where that life evolves into intelligence. The sixth factor is the fraction of intelligent civilizations that develop technology capable of sending detectable signals into space. And the seventh factor is the length of time such a civilization continues broadcasting those signals before it either destroys itself, collapses, or simply moves on to different methods of communication. When Frank Drake first ran through these numbers with his colleagues in 1961, using the best estimates available at the time, they arrived at a result suggesting there could be anywhere from 1,000 to 100 million communicating civilizations in the Milky Way alone. Modern estimates, refined with better data on star formation and planet frequency, tend to produce similarly wide-ranging results, anywhere from a handful of civilizations to millions, depending entirely on which assumptions you plug into those final three factors, the ones we understand the least. That's the real value of the Drake equation. Not a definitive number, but a map of exactly where our ignorance lives. We now have solid data for the first three factors. Star formation rates, planet frequency, and habitable zone locations are no longer guesswork. They're measured, catalogued, and refined every year through direct observation. But the final four factors, the ones dealing with the origin of life, the evolution of intelligence, the development of technology, and the longevity of civilizations, remain almost entirely unknown, resting on a sample size of exactly one known example, our own. This is why scientists find the silence so troubling. It's not that the universe seems inhospitable to life. Quite the opposite. Every new discovery over the past 50 years has pushed in the same direction, showing that the raw materials for biology are common, that liquid water is common, and that life on Earth is tougher and more adaptable than anyone once assumed. The universe looks, by every measure we have, like a place that should be bursting with living things. So, where is everyone? That question was first posed formally by the physicist Enrico Fermi during a casual lunch conversation with colleagues in 1950 at Los Alamos National Laboratory. The underlying question, however, is far older than Fermi himself. More than 2,000 years ago, the Greek philosopher Epicurus argued that since the universe was infinite and contained an infinite number of atoms, there must logically be an infinite number of other worlds. Some of them, he reasoned, inevitably similar enough to Earth to support life of their own. His student, Metrodorus of Chios, put the idea more bluntly, writing that it would be strange for a single ear of wheat to grow in an otherwise empty field, and equally strange for a single inhabited world to exist in an otherwise empty universe. The opposing view, championed by Aristotle and later reinforced for centuries by prevailing philosophical tradition, held that Earth was uniquely positioned at the center of everything, and that the very question of other worlds was somewhat beside the point. That debate remained almost entirely philosophical, with no real way to gather evidence either way, for roughly 2,000 years, until telescopes and eventually spacecraft finally gave us the tools to start investigating the question directly, rather than simply arguing about it from first principles. Fermi's contribution wasn't inventing the question of whether other worlds hold life. It was reframing that ancient philosophical debate into something closer to an engineering problem, backed by actual numbers, actual timescales, and actual physics, transforming millennia of speculation into a puzzle science could finally begin to attack directly. The group had been joking about a recent wave of reported unidentified flying objects, and the conversation drifted, as physicists' conversations sometimes do, toward the probability of extraterrestrial civilizations. According to those present, Fermi paused, did some rough calculations in his head, and then asked a simple, almost offhand question. The conversation had reportedly started with a light-hearted cartoon in a magazine depicting aliens who had stolen New York City trash cans, which led the group into a broader, more serious discussion about whether faster-than-light travel might one day be possible, and whether humanity might eventually encounter other civilizations among the stars. Fermi, known among his colleagues for his ability to produce remarkably accurate estimates from limited information, a skill so respected it's still taught today under the name Fermi estimation, apparently sat quietly through much of the conversation before abruptly changing the subject entirely, asking his now famous question in the middle of an unrelated topic, catching his lunch companions off guard. Where is everybody? It wasn't meant as a philosophical statement. It was a genuine scientific objection based on nothing more than basic arithmetic. If the galaxy is billions of years old, and civilizations capable of interstellar travel or communication should have had more than enough time to spread across it, colonize it, or at the very least announce their presence, then evidence of their existence should already be everywhere. Even at extremely conservative travel speeds, a civilization using nothing more advanced than slow, sublight spacecraft could, in principle, colonize an entire galaxy in somewhere between 5 million and 50 million years. That sounds like an enormous stretch of time, and by human standards it is. But the Milky Way is roughly 13 billion years old. 50 million years, against a backdrop of 13 billion, is less than 0.5% of the galaxy's total history. If even one civilization had emerged early, developed the technology for slow interstellar expansion, and spread outward the way bacteria spread across a petri dish, the entire galaxy should have been fully colonized many times over by now. We should see evidence of that. Structures, signals, waste heat from massive engineering projects, something. Instead, we see nothing. Not one confirmed signal, not one unambiguous artifact, not one structure that can't be explained by natural astrophysical processes. The search hasn't been small either. Since 1960, when the astronomer Frank Drake pointed a radio telescope at two nearby sun-like stars in a project called OSMA, scientists have been listening. That early experiment listened for about 150 hours before turning up nothing. Frank Drake aimed the 85-foot radio telescope at Green Bank, West Virginia, toward two nearby stars, Tau Ceti and Epsilon Eridani, hoping to catch even the faintest hint of an artificial signal. He heard nothing but static and the occasional false alarm from a passing military aircraft. But Project OSMA marked the beginning of a search that has never really stopped since. In 1974, scientists used the Arecibo radio telescope in Puerto Rico, then the largest single-dish telescope on Earth, to broadcast a deliberate message outward toward a cluster of stars called Messier 13, roughly 25,000 light-years away. The message contained basic information about humanity, our numbering system, the chemical structure of DNA, a rough diagram of our solar system, and a simple image of a human being. It was less a serious attempt at contact and more a symbolic gesture, since any reply, even if one was sent immediately, wouldn't reach us for 50,000 years. 5 years later, in 1977, NASA launched the two Voyager spacecraft, each one carrying a golden record, an actual physical disk containing sounds and images meant to represent life and culture on Earth. It held greetings, recorded in 55 different languages, music ranging from Bach to Chuck Berry, and photographs of forests, cities, and human faces. Both spacecraft have now left the solar system entirely, drifting silently through interstellar space, carrying that record with them. A message that may travel for billions of years before it ever comes anywhere close to another star system, if it ever does at all. These early efforts were symbolic as much as scientific, small gestures thrown outward into an ocean whose size we were only beginning to understand. The scientific search itself has grown far more rigorous since then. Since then, the search has grown enormously. Modern SETI programs, using far more sensitive equipment, have scanned millions of star systems across a wide range of radio frequencies. The Breakthrough Listen initiative, launched in 2015, is currently the most ambitious search ever conducted, using some of the largest radio telescopes on the planet to monitor the 1 million stars closest to Earth, along with the center of our galaxy and the disks of 100 nearby galaxies. It has already collected more data than every previous SETI search in history, combined. The project uses the Green Bank Telescope in West Virginia and the Parkes Telescope in Australia, two of the most sensitive radio observatories on the planet, along with the automated Planet Finder optical telescope at Lick Observatory in California, which searches for laser-based signals rather than radio waves. Breakthrough Listen generates more than 1 petabyte of data every single day, an amount so large that researchers rely heavily on machine learning algorithms just to sift through it, flagging unusual signals for human review rather than requiring scientists to comb through the raw data by hand. Separately, the Allen Telescope Array, a dedicated collection of 42 radio dishes in Northern California, was built specifically for SETI research and funded partly through private donations. It continues scanning the sky around the clock, targeting stars known to host planets, along with regions of interest like the galactic center. Every one of these instruments represents a dramatic leap in capability compared to Frank Drake's single-dish search back in 1960. And yet, even combined, they still represent only a small fraction of the sky, a limited slice of possible frequencies, and a search that has been running, in cosmic terms, for barely the blink of an eye. And so far, the result has been consistent. Silence. There have been a handful of tantalizing signals over the decades. The most famous is the WOW signal, detected in 1977 by a radio telescope in Ohio, a burst of narrowband radio emission that matched almost exactly what scientists expected an artificial signal might look like. It lasted about 72 seconds, was never repeated despite years of follow-up observation, and remains unexplained to this day. The signal was detected by the Big Ear Radio Telescope at Ohio State University. It was so unusual, so closely matching the theoretical signature of an artificial transmission, that the astronomer reviewing the printout, Jerry Eman, circled the data on the page and wrote the word "WOW" in red ink beside it, giving the signal its lasting name. The signal arrived at almost exactly the frequency of 1,420 MHz, a frequency associated with neutral hydrogen, the most common element in the universe. Many SETI researchers had long theorized this would be a logical, universally recognizable frequency for any civilization attempting to attract attention across the galaxy. Any species capable of radio astronomy would likely already be familiar with that exact frequency from studying hydrogen clouds in their own galaxy. Some researchers have proposed it was caused by a passing comet releasing a burst of hydrogen gas, a natural explanation that fits some of the data, but not all of it. Others still consider it genuinely unresolved. But one signal, seen once and never repeated in nearly 5 decades of continued listening, is not evidence of a civilization. It's a mystery, filed away, unresolved, one data point in an otherwise empty dataset. This is the Great Silence. Decades of listening. Millions of stars scanned. Billions of radio frequencies monitored. And nothing that rises to the level of confirmed contact. Given how common the ingredients for life appear to be, given how much time the universe has had, given how quickly even a slow-moving civilization should theoretically be able to spread, that silence demands an explanation. Scientists have proposed dozens of possible solutions to the Fermi paradox over the decades. Tonight, we're going to walk through the most serious ones, the ones that have survived scrutiny and remain part of active scientific debate. The first major category of explanations falls under something called the rare earth hypothesis. This idea suggests that, while the basic chemical ingredients for life might be common, the specific combination of conditions required for complex, intelligent life to emerge and survive long enough to build a civilization might be extraordinarily rare. Simple life, microbes, single-celled organisms might indeed be common throughout the universe, exactly as the chemistry suggests it should be. But the jump from simple life to complex, multicellular, intelligent life might require a chain of coincidences so specific that it has only happened once, here on Earth. Consider what Earth actually had to get right. Our planet orbits a star that has remained remarkably stable for more than 4 billion years, producing a steady, predictable output of energy, without the violent flares that many smaller, more common red dwarf stars regularly unleash on their orbiting planets. This matters more than it might first appear, because red dwarf stars are by far the most common type of star in the galaxy, meaning most of the potentially habitable planets we've discovered so far actually orbit these smaller, cooler stars, rather than sun-like ones. The trouble is that red dwarfs, despite their small size and low overall energy output, tend to be far more magnetically active and prone to violent flaring than larger stars like our Sun, particularly during the first billion years or so of their extremely long lifespans. A planet close enough to a red dwarf to sit within its habitable zone would also be close enough to be regularly bombarded by these flares. That's true, because these stars are so dim, the habitable zone has to sit in close. The flares release powerful bursts of radiation and charged particles capable of stripping away a planet's atmosphere over time. This is exactly the kind of process that may have already stripped the atmospheres from some of the inner TRAPPIST-1 planets. This creates a difficult trade-off. Red dwarf stars are common, long-lived, and host plenty of planets in their habitable zones. But the very habitability of those zones may be undermined by the star's own volatile behavior, leaving many of the most numerous potentially habitable worlds in the galaxy less hospitable than they first appear. Earth sits at almost exactly the right distance from that star, close enough for liquid water, far enough to avoid a runaway greenhouse effect like the one that turned Venus into a furnace, with surface temperatures hot enough to melt lead. Earth has a large moon, unusually large relative to the size of its host planet, formed billions of years ago when a Mars-sized object collided with the young Earth. That moon does more than create ocean tides. It stabilizes Earth's axial tilt, preventing the kind of chaotic wobbling that would otherwise send our climate swinging unpredictably between extremes over geological timescales, making it far harder for complex ecosystems to establish themselves and persist. Earth has plate tectonics, a slow, grinding recycling system that regulates carbon dioxide levels in the atmosphere over millions of years, acting as a planetary thermostat that has kept our climate within survivable bounds for billions of years, even as the sun has grown gradually brighter. This process works because Earth's outer shell is broken into roughly a dozen major moving plates, drifting atop a hotter, more pliable layer of rock beneath them, at speeds roughly comparable to the rate your fingernails grow. Where plates collide, one is often forced downward, in a process called subduction, dragging carbon-rich rock and sediment deep into the planet's interior, where heat and pressure eventually release that carbon back into the atmosphere through volcanic activity, completing a cycle that takes hundreds of millions of years to run its full course. This slow, continuous recycling prevents carbon dioxide from either building up into a runaway greenhouse effect, as happened on Venus, or being permanently locked away and lost, which would eventually starve the atmosphere of the greenhouse warming needed to keep water liquid. Very few rocky planets we've discovered so far show clear evidence of active plate tectonics. Earth has a strong magnetic field generated by the churning motion of molten iron in its core, a field that deflects the bulk of the sun's charged particles and cosmic radiation, protecting both the surface and the atmosphere itself from being gradually stripped away. Mars, by comparison, lost its own magnetic field billions of years ago. With it went most of its atmosphere, leaving behind the cold, thin, radiation-blasted world we see today. Evidence gathered by rovers like Curiosity and Perseverance strongly suggests that early Mars, roughly 3.5 to 4 billion years ago, once had rivers, lakes, and possibly even a shallow ocean covering part of its northern hemisphere, along with an atmosphere thick enough to support liquid water on the surface. Something changed. Without a strong magnetic field to protect it, the sun's charged particles gradually stripped away that atmosphere over hundreds of millions of years. And as atmospheric pressure dropped, the liquid water still present either froze into the polar caps and subsurface ice or evaporated and was lost to space entirely. Mars may have had a genuine window of habitability, possibly even long enough for simple life to emerge, before that window closed permanently. If so, it stands as a sobering example of just how easily a planet can lose the conditions needed to sustain life, even after starting out with real promise. Venus offers an even starker warning. Roughly the same size as Earth, orbiting at a distance that might once have allowed liquid water, Venus instead became a runaway greenhouse world. Its thick atmosphere of carbon dioxide traps heat so effectively that surface temperatures now reach roughly 460 degrees Celsius, or about 860 degrees Fahrenheit, hot enough to melt lead. Atmospheric pressure at the surface is roughly 90 times greater than Earth's. Whatever water Venus once had, and there's some evidence it may have had oceans of its own billions of years ago, is long gone now, broken apart by intense heat and stripped away into space. Two planets, both roughly Earth-sized, both sitting reasonably close to our Sun's habitable zone, and both ultimately hostile to life as we understand it. Earth, sitting between them, somehow got the balance right and has kept it right for more than 4 billion consecutive years. And then there's Jupiter, sitting far out in the outer solar system, its immense gravity acting as something of a cosmic bodyguard, deflecting or capturing many of the comets and asteroids that might otherwise find their way into the inner solar system and collide with Earth. And then there's Jupiter, sitting far out in the outer solar system, its immense gravity acting as something of a cosmic bodyguard, deflecting or capturing many of the comets and asteroids that might otherwise find their way into the inner solar system and collide with Earth. Beyond these structural factors, Earth's biological history itself has been anything but smooth. Roughly 700 million years ago, evidence suggests our planet went through what scientists call a snowball Earth event, a period when glaciers may have extended all the way to the equator, encasing the entire planet in ice for tens of millions of years at a stretch. Geologists first pieced together evidence for this event by finding glacial deposits, rock formations left behind by moving ice, in regions that were located near the equator at the time those deposits formed. That location was determined based on the magnetic alignment of minerals within the rock itself. It was a finding that seemed almost impossible until researchers realized it meant the entire planet, equator included, had once been frozen solid. Some researchers believe there may have been several such episodes, separated by warmer periods, stretching across a span of hundreds of millions of years, each one a potential near-total reset for whatever complex life had managed to establish itself beforehand. Life survived, clinging on in isolated pockets of liquid water, perhaps near volcanic vents or beneath thinning ice at the equator, but it was a near-catastrophic bottleneck, one that could easily have ended differently. Even earlier, roughly 2.4 billion years ago, an event called the Great Oxidation Event reshaped the entire planet when photosynthetic microbes began pumping oxygen into an atmosphere that had never contained more than trace amounts of it before. For the anaerobic organisms that dominated Earth at the time, oxygen was a poison, and the sudden rise in its concentration triggered what may have been the first mass extinction in the planet's history, wiping out huge portions of existing microbial life. And yet, that same crisis opened the door for entirely new forms of biology. Aerobic organisms capable of using oxygen to generate far more energy than anaerobic metabolism ever could. It eventually set the stage, billions of years later, for the complex, energy-hungry life that would include animals, and eventually us. Every one of these factors, a stable star, a well-placed orbit, a stabilizing moon, active plate tectonics, a protective magnetic field, a gravitational shield in the outer solar system, had to align. And they had to remain aligned for billions of consecutive years in order for complex life to have the uninterrupted stability it needed to evolve. Change any single one of those variables, and the story of Earth could have played out very differently. A planet without a large moon might tumble chaotically through wild climate swings. A planet without plate tectonics might slowly cook itself through an unchecked greenhouse effect, the way Venus did. A planet without a magnetic field might have its atmosphere stripped away by stellar radiation over a few 100 million years. If even one of these conditions is genuinely rare on a galactic scale, the number of planets capable of supporting the billions of years of stability required for intelligent life to emerge could shrink dramatically, from 6 billion potential candidates down to perhaps a mere handful, scattered across an entire galaxy. This is one possible answer to the paradox. Not that life itself is rare, but that the specific staircase leading from simple microbes to intelligent technological civilizations is narrow, fragile, and easily broken at any one of a dozen different steps. This idea connects to a broader concept scientists call the Great Filter. Earth's own evolutionary history offers some sobering context for this idea. Life on Earth appears to have begun remarkably quickly, with the earliest evidence of microbial life dating back roughly 3.7 billion years, just a few 100 million years after the planet's surface had cooled enough to support liquid water at all. That fast start suggests simple life might not be a particularly difficult step to achieve once the right chemistry and conditions are in place. But then, something strange happens in the fossil record. For roughly 2 billion years after that, life on Earth remained almost entirely single-celled. No complex organisms. No multicellular structures. Just an almost unimaginably long stretch of simple bacteria and archaea, dominating the planet with no significant increase in complexity, despite having billions of years and an entire planet's worth of environments to experiment in. It wasn't until around 1.5 billion years ago that the first more complex eukaryotic cells appear in the fossil record, likely arising from one simple cell engulfing another in a partnership that eventually became permanent, the ancestor of every plant, animal, and fungus alive today. This event, known as endosymbiosis, appears to have happened only once in the entire 4 billion-year history of life on Earth. It was a single successful merger between two separate microbial cells that somehow avoided destroying each other and instead formed a permanent, mutually beneficial partnership. One cell eventually became the energy-producing mitochondria found inside nearly every complex cell alive today. If that merger really did happen only once, despite countless trillions of microbial cells interacting with each other across more than 1 billion years beforehand, it suggests this particular step might be extraordinarily improbable, a lucky accident rather than an inevitable outcome of evolution, and one that might simply never occur at all on many other worlds, no matter how much time is available. Multicellular life itself didn't become common until roughly 600 million years ago. complex animal life, the kind capable of movement, sensory organs, and eventually intelligence, didn't truly explode in diversity until the Cambrian explosion, roughly 540 million years ago. That was a geologically brief period, lasting somewhere between 13 and 25 million years. During that window, nearly every major animal body plan still seen today first appears in the fossil record, seemingly out of nowhere, following billions of years of comparatively simple life. That means, for more than 80% of the entire history of life on Earth, our planet hosted nothing more advanced than single-celled microbes. If that pattern holds true elsewhere in the universe, and there's no obvious reason to assume Earth's timeline is unusually slow, then the jump from simple life to complex life might be the single hardest step in the entire chain. It could be a bottleneck so severe that most planets harboring life never make it past that stage at all, remaining forever populated by nothing more than microscopic organisms drifting in oceans no one will ever observe. Even after complex, intelligent animal life did eventually emerge on Earth, technology itself turns out to be a remarkably rare outcome. Earth has hosted an enormous diversity of intelligent species over the course of its history. Dolphins and other cetaceans display complex social behavior, problem-solving, and what appears to be a form of individual identity, recognizing themselves in mirrors and communicating through distinct, individualized calls that function almost like names. Octopuses solve complex puzzles, use tools, and display remarkable problem-solving abilities, despite having a nervous system so different from ours that much of it is distributed throughout their arms rather than centralized in a single brain, representing an entirely independent evolutionary path toward intelligence, separated from our own by more than 500 million years of divergent evolution. Crows and other corvids manufacture and use tools, plan for future events, and have demonstrated reasoning abilities that rival those of young children in certain controlled experiments. And yet, out of the millions of species that have existed throughout Earth's history, only one, our own, ever developed the specific combination of traits needed for technology. Opposable thumbs capable of fine manipulation, a larynx capable of producing complex speech, a level of social cooperation sufficient to transmit knowledge across generations, and an environment that rewarded tool use and problem-solving over countless generations. That combination eventually led to agriculture, writing, mathematics, and ultimately, radio telescopes pointed at the stars. If intelligence itself is not rare, but the specific evolutionary path toward technology is, then a planet could easily be teeming with complex, even remarkably intelligent life. Dolphins, octopuses, crows, and creatures we can't yet imagine could all exist there, without ever producing a single radio signal, a single spacecraft, or a single civilization capable of being detected across interstellar distances. This possibility fits neatly into the broader idea known as the Great Filter. Even after complex life did finally establish itself on Earth, its continued existence has been anything but guaranteed. The fossil record shows at least 5 major mass extinction events over the past 500 million years, each one wiping out a substantial fraction of all species alive at the time. The most severe of these, known as the Permian extinction, occurred roughly 252 million years ago, likely triggered by massive volcanic eruptions in a region of Siberia that released enormous quantities of carbon dioxide and other gases into the atmosphere over a relatively short geological period. acidifying oceans and disrupting climate patterns worldwide. Scientists estimate that as much as 96% of all marine species and roughly 70% of terrestrial vertebrate species were lost during that event. Complex life on Earth came remarkably close to being reset back to something far simpler. The most recent mass extinction, roughly 66 million years ago, is the one most people are familiar with. It was caused by an asteroid roughly 6 miles wide, striking what is now the Yucatan Peninsula in Mexico, releasing energy equivalent to billions of nuclear weapons detonating simultaneously. That triggered wildfires, tsunamis, and a prolonged period of darkened skies that collapsed food chains around the planet. That impact ended the age of the dinosaurs and cleared the way for small, previously marginal mammals to eventually diversify into the dominant group of land animals on the planet, eventually including primates, and eventually us. Had that asteroid arrived a few hours earlier or later in Earth's rotation, striking deep ocean water instead of the shallow, sulfur-rich rock it actually hit, the climate effects might have been far less severe. The dinosaurs might never have gone extinct at all, leaving mammals in the marginal role they had occupied for well over 100 million years, with no clear path toward the eventual rise of intelligent, technological life. Complex, intelligent life on Earth is not the product of a smooth, inevitable upward climb. It's the product of a long series of near misses, catastrophic resets, and improbable strokes of good fortune, any one of which could easily have gone differently. The theory proposes that somewhere along the evolutionary path, from non-living chemistry to a civilization capable of spreading across the stars, there exists at least one barrier so difficult to overcome that almost nothing manages to pass through it. The unsettling part of the great filter idea is that we don't know where that barrier sits. It could be behind us, meaning humanity has already passed through the hardest step, and we are, against overwhelming odds, one of the rare success stories. If that's the case, the universe truly might be mostly empty. It could be filled with simple microbial life on countless worlds, but almost devoid of anything more advanced, because the leap from simple life to complex life, or from complex life to intelligence, is so improbable that it rarely happens twice. That would be the hopeful version of the great filter. It would mean our future, while uncertain, is at least not doomed by some universal law that destroys civilizations before they can spread. But there's a darker possibility. The filter could be ahead of us. Something that every sufficiently advanced civilization eventually runs into. A barrier so consistent, so universal, that it wipes out every species before it manages to become visible across interstellar distances. If that's the case, the silence we observe isn't evidence that intelligent life is rare. It's evidence that intelligent life doesn't survive very long once it appears. This possibility has driven some of the more sobering research into what such a filter might actually look like. One candidate is self-inflicted destruction through advanced technology. The same scientific progress that allows a civilization to build radio telescopes and consider interstellar travel also, almost inevitably, grants that civilization the tools for large-scale destruction. Nuclear weapons, engineered pathogens, runaway, artificial intelligence, catastrophic climate disruption caused by industrial activity. Humanity itself has already lived through more than 7 decades under the shadow of nuclear weapons capable of ending civilization within hours. We came alarmingly close to nuclear conflict on more than one occasion during the Cold War, sometimes due to nothing more than a malfunctioning early warning system or a single officer's judgment call in the middle of the night. In September of 1983, a Soviet early warning satellite system reported that the United States had launched 5 intercontinental ballistic missiles. Protocol called for an immediate retaliatory strike. The officer on duty that night, Stanislav Petrov, judged the alert to be a false alarm based on little more than intuition and the fact that an attack of only 5 missiles seemed strategically unlikely, and chose not to report it up the chain of command. He was right. The satellite had mistaken sunlight, reflecting off high-altitude clouds for the heat signature of missile launches. One person's judgment call, in a moment lasting only minutes, may have prevented a nuclear exchange that could have ended civilization as we know it. If a similarly advanced civilization elsewhere in the universe reaches a comparable stage of technological development, it likely faces the same challenge we do. Weapons capable of planetary-scale destruction, paired with the same evolutionary instincts for tribalism, competition, and short-term thinking that shaped their biology. The odds of navigating that period successfully, every single time, for every single civilization, start to look uncomfortably slim. Beyond nuclear weapons, modern researchers have identified other potential extinction-level risks that any sufficiently advanced civilization is likely to eventually create for itself. Engineered pathogens, designed either for research or as weapons, capable of spreading faster and more lethally than anything found in nature. Runaway artificial intelligence, systems built to pursue a goal with such single-minded efficiency that they act against the interests of their creators in ways nobody anticipated. Catastrophic, self-inflicted climate disruption caused by the very industrial processes that allowed a civilization to develop advanced technology in the first place. Humanity's own experience with this risk is still unfolding. Since the beginning of industrialization roughly 2 centuries ago, atmospheric carbon dioxide concentrations have risen from around 280 parts per million to over 420 parts per million today. That's a change large enough to measurably warm the planet's average temperature, shift weather patterns, and raise sea levels. And it happened within a period representing a tiny fraction of 1% of the time modern humans have existed as a species. Whether humanity successfully manages this transition, shifting toward energy sources that don't destabilize the climate that has allowed civilization to flourish for the past 10,000 years, remains an open and actively contested question, one that will likely be answered within the lifetimes of people alive today. If any sufficiently industrialized civilization faces a similar challenge, a narrow window in which its own technological success threatens to undermine the very environmental stability that made that success possible in the first place. Then this too could function as a filter, quietly narrowing the number of civilizations that make it through to a long-term, stable, spacefaring future. None of these risks are certainties. But if even a modest fraction of technological civilizations fail to navigate this period safely, one filter, repeated over and over across billions of star systems, could explain the silence all on its own. If most technological civilizations discover the physics of nuclear fission, or something equally destructive at roughly the same point in their development, and if even a modest fraction of them fail to navigate that period safely, the window during which a civilization is both capable of communicating across space and stable enough to keep doing so might be extremely short. Humanity's own experience offers a rough sense of just how tight that window can be. Radio communication became widespread only in the early 20th century, and functional nuclear weapons arrived barely 4 decades later. Meaning our species has only had the technological ability to broadcast its presence into the galaxy for roughly the same length of time. It has also possessed the ability to destroy itself entirely. If that pattern, communication and self-destructive capability arriving in close succession, turns out to be common among technological civilizations generally, then the margin for error during this fragile transitional period may be thinner than most people assume. Cosmically speaking, a civilization that survives for only a few hundred years after developing radio technology, before destroying itself or collapsing back into a pre-industrial state, would be virtually invisible. Radio signals fade with distance. Our own television and radio broadcasts, leaking unintentionally into space since the early 20th century, have only traveled roughly 100 light-years outward so far, a genuinely tiny distance compared to the 100,000 light-year width of the Milky Way. It's worth noting that even those signals are already growing fainter and harder to detect than they once were. Older analog television and radio broadcasts, the kind that leaked powerfully and continuously into space for decades, have increasingly been replaced by digital signals and cable or satellite-based transmission, many of which are far more efficient and leak far less energy outward into the surrounding galaxy. In a strange way, humanity may be becoming quieter from the perspective of an outside observer, even as our population and technology continue to grow. If that pattern holds true for other civilizations as well, each one only broadcasting detectable, leaky signals for a brief technological phase before switching to more efficient, less detectable methods of communication, then the total volume of accidentally detectable radio noise in the galaxy at any given moment might be far smaller than early SETI researchers originally assumed. If most civilizations only broadcast detectable signals for a brief window measured in centuries, rather than millions of years, then the odds of 2 civilizations existing at the same time, within range of each other, and happening to be listening at exactly the right moment, become vanishingly small. It's a bit like trying to spot 2 matches being struck at random points across an enormous dark field, each one burning for only a fraction of a second before going out. Even if thousands of matches are lit over the course of an evening, the odds that any 2 of them happen to flare at the exact same instant, close enough to see one another, are extremely low. This leads to another proposed solution, sometimes called the zoo hypothesis. This idea suggests that advanced civilizations do exist, and may even be aware of us, but have deliberately chosen not to make contact, perhaps observing humanity the way a conservation park might observe wildlife, from a careful distance, without interference. The zoo hypothesis is difficult to test, and many scientists consider it unfalsifiable, since it essentially predicts the exact silence we already observe, regardless of what's actually happening. Some versions of this idea go further, suggesting the reason might not be scientific curiosity at all, but something closer to a deliberate policy. It would be a kind of galactic agreement among older civilizations to avoid interfering with younger species until they reach a certain threshold of technological or social maturity, similar in spirit, though not in seriousness, to the fictional idea of a prime directive. Critics of the zoo hypothesis point out that it requires near-perfect coordination among what would presumably be an enormous number of independent civilizations, all agreeing to the same policy of silence, and all successfully enforcing it across the entire galaxy, without a single exception or violation over millions of years. That level of coordination seems difficult to imagine, even among a single species, let alone across countless independent alien ones. A related but darker version of this idea is sometimes called the dark forest hypothesis, drawn from science fiction but taken seriously as a thought experiment by some researchers. It suggests that the universe is silent, not because civilizations are rare, but because broadcasting your presence is dangerous. In this scenario, every civilization understands that announcing its location to the galaxy carries enormous risk, since any sufficiently advanced and hostile neighbor could, in theory, use that information to eliminate a competitor before it becomes a threat. Under this logic, the safest strategy for any civilization is silence. Stay quiet. Listen, but never transmit. If every civilization independently reaches the same conclusion, the entire galaxy falls silent, not because it's empty, but because everyone inside it has learned to hide. Critics of this idea point out that it assumes hostile intent is the default outcome of contact between civilizations, an assumption that's impossible to verify, with a sample size of exactly one known civilization, our own. It also assumes that hiding is actually possible for a sufficiently advanced species, given that any civilization industrious enough to expand across multiple star systems would likely produce detectable waste heat, atmospheric changes, or other physical signatures, regardless of whether it intended to broadcast its presence. Still, the underlying logic that the incentives facing an advanced civilization might favor caution over broadcasting remains a serious consideration among researchers studying what's sometimes called messaging extraterrestrial intelligence, the more provocative counterpart to simply listening. Some scientists have argued we shouldn't be transmitting deliberate messages into space at all, given how little we understand about what might be listening, while others argue that any civilization capable of reaching us would already be technologically capable of finding us, regardless of whether we announce ourselves, making the caution largely irrelevant. This debate became especially prominent following a series of deliberate messages sent by a Russian-led group in the 2010s, transmitted from a radar facility in Crimea towards several nearby, potentially habitable star systems without any broad international consultation beforehand. Prominent scientists, including the late physicist Stephen Hawking, publicly warned against this kind of unilateral messaging. They argued that history's own record of contact between technologically unequal civilizations here on Earth offered little reassurance about how a similar imbalance might play out on an interstellar scale, since more advanced societies have often caused enormous harm to less advanced ones they encountered. Others countered that the entire debate may be moot, since Earth has already been leaking radio and television signals into space for more than a century, meaning any civilization advanced enough to pose a genuine threat would likely have detected us long before any deliberate message was ever sent. This remains a speculative idea, difficult to prove or disprove, but it illustrates just how many different explanations can account for the same simple observation: an empty sky and a silent radio spectrum. There's also a more mundane possibility worth taking seriously: the idea that we simply haven't searched long enough, or in the right way, to find anything yet. A related idea, sometimes discussed alongside the search for technosignatures, is the possibility that advanced civilizations don't remain biological, or even remain interested in expansion and communication for very long after developing sufficiently powerful technology. Some researchers have speculated that once a civilization masters artificial intelligence and advanced computing, it may increasingly turn its attention inward, towards simulated or virtual environments capable of providing experiences and forms of existence potentially far richer and more efficient than physically colonizing hostile, distant star systems. Under this line of reasoning, a truly advanced civilization might have little practical interest in building enormous, energy-hungry structures visible across interstellar distances, or in broadcasting messages to worlds it has no pressing need to contact. It might instead choose a quieter, more self-contained existence that would leave few, if any, detectable traces for outside observers like us. This remains highly speculative, resting on assumptions about the motivations of minds and civilizations radically different from our own. And it's difficult to test or verify in any rigorous way. But it represents yet another possible explanation for why an otherwise busy, expanding galaxy might still appear completely silent from our vantage point. Consider the scale of the problem honestly. Even the most ambitious SETI programs to date have only managed to scan a small fraction of the sky across a limited slice of the radio spectrum for a relatively short period of time, measured in decades rather than centuries. The astronomer Jill Tarter, one of the pioneers of the modern search for extraterrestrial intelligence, once compared the entire history of SETI research to scooping a single glass of water from Earth's oceans and concluding, based on that one glass, that the ocean contains no fish. Tarter spent decades leading SETI research efforts, and her work later inspired the character of Ellie Arroway in the novel and film Contact. That helped bring public attention to a field that, for much of its history, struggled to secure consistent funding. The effort was famously defunded by the United States Congress in 1993, just 1 year after NASA had begun a formal, government-backed search program. It continued instead through private donations and universities for the following 3 decades. It's an apt comparison. The volume of space, the range of possible frequencies a civilization might use to communicate, and the sheer number of stars that would need to be observed, all combine to make this one of the most difficult searches ever attempted by science. We might simply be looking in the wrong place, at the wrong time, using the wrong method. Radio waves might not even be the preferred communication method for an advanced civilization. A species far more advanced than our own might rely on tightly focused laser communication, quantum entanglement-based signaling, or some technology we haven't even conceived of yet, none of which would show up in a conventional radio telescope survey. This brings us to a newer and increasingly important frontier in the search, something scientists call technosignatures. Rather than waiting passively for a deliberate signal, researchers are now searching for indirect evidence of technology, the accidental byproducts that any sufficiently advanced civilization might leave behind, whether they intend to or not. This includes searching for unusual patterns of waste heat from massive engineering projects, unexpected chemical signatures in a planet's atmosphere that couldn't be produced by natural processes, or strange dimming patterns around distant stars that might suggest large-scale artificial structures. This includes searching for unusual patterns of waste heat from massive engineering projects, unexpected chemical signatures in a planet's atmosphere that couldn't be produced by natural processes, or strange dimming patterns around distant stars that might suggest large-scale artificial structures. One of the more famous theoretical concepts driving this search is the idea of a Dyson sphere, first proposed by the physicist Freeman Dyson in 1960. Dyson reasoned that any sufficiently advanced civilization, faced with growing energy demands, would eventually want to capture a much larger fraction of its home star's total energy output than a single planet ever could. The most efficient way to do that, he suggested, would be to construct a vast swarm of satellites, solar collectors, or habitats encircling the star itself, capturing its light before it ever has a chance to escape into space. Such a structure wouldn't need to be a solid shell, which would be structurally impossible to build and maintain. It would more likely be a loose swarm of countless individual objects orbiting at different distances and angles, gradually capturing more and more of the star's energy over time. From a great distance, a star surrounded by such a swarm would look unusual, its visible light dimmed by the structures blocking it, while its infrared signature would likely spike, as all that captured energy is eventually re-radiated as waste heat. This is precisely the kind of signature astronomers have started searching for, scanning large catalogues of stars for exactly this mismatch: dim in visible light, unusually bright in infrared, a pattern that would be very difficult to explain through natural processes alone. So far, no confirmed candidates have been found. In October of 2017, astronomers detected an object called Oumuamua, the first confirmed visitor from outside our solar system ever observed passing through it, an elongated, reddish object, roughly the size of a football field, moving on a trajectory that clearly showed it had originated from another star system entirely. Its unusual, cigar-like shape, along with a slight, unexplained acceleration as it left the solar system that couldn't be fully accounted for by the sun's gravity alone, led a small number of researchers to speculate about its origin. Most notably, the Harvard astronomer Avi Loeb publicly suggested it might be an artificial object, perhaps a discarded piece of alien technology, rather than a natural comet or asteroid. The vast majority of the scientific community disagreed, favoring natural explanations, most likely outgassing of frozen hydrogen or nitrogen from the object's surface, invisible to our telescopes, but capable of producing the small thrust needed to explain its trajectory. Oumuamua was only observable for a few months before it became too faint and distant to study further, leaving many of the specific questions about its exact composition and shape permanently unresolved. Whatever it actually was, its discovery confirmed something important: that objects from other star systems do occasionally pass through our own. It opened an entirely new category of search, with scientists now actively watching for the next interstellar visitor, hoping to study it more thoroughly before it, too, disappears back into the depths of space. But the search itself represents a shift in strategy, moving beyond simply listening for deliberate messages and instead looking for the accidental, unavoidable fingerprints that any sufficiently large-scale civilization might leave on its environment, whether it wants to be found or not. One particularly famous case involved a star called KIC 8462-852, nicknamed Tabby's star, discovered through the Kepler Space Telescope. This star exhibited unusual, irregular dimming patterns, sometimes dropping in brightness by as much as 22%, far beyond what a simple planet passing in front of it could explain. For a brief period, some researchers speculated it might be evidence of a massive artificial structure, something like a Dyson swarm, a hypothetical megastructure built by an advanced civilization to capture a significant fraction of its star's energy output. Years of further observation eventually pointed toward a more mundane explanation, likely uneven clouds of dust orbiting the star. But the case illustrates the kind of evidence scientists are now actively watching for, and it demonstrates that our tools have grown sensitive enough to detect exactly this sort of anomaly, should a genuine one ever appear. Meanwhile, the search for simpler forms of life, rather than intelligent civilizations, has entered an entirely new era. The James Webb Space Telescope, launched in December of 2021, has begun analyzing the atmospheres of exoplanets in unprecedented detail, searching for what scientists call biosignatures, chemical fingerprints that could indicate biological activity. Webb's primary mirror measures roughly 21 feet across, assembled from 18 individual hexagonal segments, coated in a microscopically thin layer of gold to maximize its ability to capture infrared light. It orbits not Earth directly, but a gravitationally stable point, roughly 1 million miles away, called the second Lagrange point. There, the combined gravity of the Sun and Earth allows a spacecraft to maintain a consistent position with minimal fuel expenditure. Its infrared sensitivity, far greater than that of its predecessor, the Hubble Space Telescope, allows it to detect the extremely faint dip in starlight caused when a planet passes in front of its star. It can then analyze exactly which wavelengths of that light have been absorbed by the planet's atmosphere on the way through, revealing the chemical composition of worlds light years away, one faint signal at a time. On Earth, our atmosphere contains a highly unusual mixture of oxygen and methane existing together, a combination that shouldn't persist naturally since the two gases react with each other and should cancel out over relatively short geological timescales. Oxygen itself, once considered the gold standard biosignature, has turned out to be more complicated than early researchers assumed. Certain planets, particularly those orbiting close to their stars, can generate oxygen through entirely non-biological processes. When intense stellar radiation breaks apart water molecules in the upper atmosphere, allowing the lighter hydrogen to escape into space while the heavier oxygen remains behind and gradually accumulates. A planet could, in principle, build up a thick, detectable oxygen atmosphere without a single living organism ever existing on its surface, simply through this kind of runaway photochemical process. This is part of why scientists now insist on looking for oxygen alongside other gases, like methane, that wouldn't be expected to coexist with it unless something was actively producing both at once. The only reason Earth's atmosphere maintains this seemingly unstable balance is that living organisms are constantly replenishing both gases, plants, and photosynthetic microbes producing oxygen, other organisms producing methane. If astronomers detected a similar chemical imbalance in the atmosphere of a distant exoplanet, it would be one of the strongest possible pieces of indirect evidence for life, without ever needing to send a probe or receive a deliberate signal. In 2023, researchers using the James Webb Telescope detected traces of what might be dimethyl sulfide in the atmosphere of a planet called K218b, a compound that, on Earth, is produced almost exclusively by marine phytoplankton. A follow-up observation strengthened the case somewhat, but a series of independent research teams who later reanalyzed the same data reached a more cautious conclusion, finding the signal too weak and too easily explained by other non-biological molecules to count as reliable evidence. K218b belongs to a category of worlds astronomers now call Hycean planets, a term combining the words hydrogen and ocean, describing planets thought to host deep, global oceans beneath a thick, hydrogen-rich atmosphere. If confirmed, these worlds could represent an entirely new category of potentially habitable environment, quite different from the rocky, thin atmosphered planets, like Earth, that most habitability searches originally focused on. The James Webb Telescope has also turned its instruments toward the TRAPPIST-1 system, attempting to determine whether any of its 7 rocky planets retain meaningful atmospheres at all. A critical question, given how close they orbit their small, occasionally violent host star. Early results for some of the innermost planets suggest they may have lost most or all of their original atmospheres, stripped away by stellar radiation over billions of years. A sobering reminder that a planet sitting in the habitable zone doesn't guarantee it actually holds on to the atmosphere needed to keep water liquid on its surface. Observations of the outer TRAPPIST planets are ongoing and represent one of the most closely watched habitability investigations currently underway. Looking further ahead, NASA has begun early design work on a mission called the Habitable Worlds Observatory, a space telescope specifically designed to directly image Earth like planets orbiting Sun-like stars, rather than relying solely on the indirect transit method used by Kepler and TESS, and to analyze their atmospheres in search of biosignatures with far greater precision than even Webb currently allows. Ground-based astronomy is advancing as well. The extremely large telescope is currently under construction in the Atacama Desert in Chile. It will feature a primary mirror spanning roughly 130 feet across, composed of nearly 800 individual segments. That will make it by far the largest optical telescope ever built once it becomes operational later this decade, with light-gathering power far exceeding anything currently available from the ground. Between missions like these and the continued expansion of radio and optical SETI surveys, the coming decades represent what many astronomers consider the most promising window yet in the search for answers, a period during which humanity's ability to actually detect life, rather than simply theorize about it, is expanding faster than at any previous point in history. Closer to home, missions are also being prepared to search directly for life within our own solar system. The Europa Clipper mission, launched in October of 2024, is currently traveling toward Jupiter's icy moon Europa, where it will study the subsurface ocean believed to lie beneath the moon's frozen crust, an ocean that may contain more liquid water than every ocean on Earth combined. If simple life exists anywhere close to home, radiating outward from hydrothermal vents on the floor of that hidden ocean, similar to the vent ecosystems found deep in Earth's own oceans, Europa may be one of our best chances of confirming it within our lifetimes. Mars remains under close scrutiny as well. Since landing in February of 2021, the Perseverance rover has been exploring Jezero Crater, an ancient lakebed that once held a river delta, collecting rock and soil samples specifically chosen for their potential to preserve signs of ancient microbial life, if any, ever existed there. Those samples are being carefully sealed and stored on the Martian surface, part of an ambitious, multi-mission campaign developed jointly by NASA and the European Space Agency, intended to eventually retrieve them and bring them back to Earth, where laboratories far more sensitive and sophisticated than anything that can be sent to Mars could analyze them directly. That mission has faced repeated delays and cost overruns, and its exact timeline remains uncertain. But if it succeeds, it would mark the first time in human history that scientists have had the opportunity to directly examine material from another planet, collected specifically with the search for ancient life in mind. So, where does this leave us? There's one more possibility worth taking seriously before we close. An idea that doesn't require civilizations to be rare, or fragile, or hidden, or self-destructive. It simply requires that we, as a species, arrived unusually early. The universe is currently about 13.8 billion years old. That sounds ancient, and by human standards it is. But stars, the very engines that make life possible, are going to keep forming for an almost unimaginably longer stretch of time still ahead of us. Small, cool, red dwarf stars are the most common type of star in the universe, making up roughly 75% of all stars in the Milky Way. They burn their hydrogen fuel so slowly and efficiently that some of them are expected to remain stable, shining steadily, for trillions of years into the future. Trillions, not billions. Our own Sun, a fairly average, mid-sized star, will only last around 10 billion years total before it exhausts its fuel and swells into a red giant. That means the era of star formation, the period during which new stars and their accompanying planets are still being born, has barely gotten started. Some astronomers estimate that more than 90% of all the stars the universe will ever produce haven't formed yet. If that estimate is even roughly correct, then Earth and humanity arrived somewhere near the very beginning of the timeline, during which life could exist at all. Not somewhere in the middle or toward the end, as our instinct might otherwise suggest. Under this framework, the silence we observe isn't necessarily evidence that intelligent life is impossible or even particularly rare in an absolute sense. It might simply mean that intelligent, technological life is an extremely early phenomenon in cosmic history, and that the vast majority of civilizations the universe will ever produce simply haven't had the time to appear yet. We may not be late to a crowded party. We may be among the very first guests to arrive at one that's only just beginning. This is, in its own way, one of the more hopeful explanations for the paradox. It suggests that rather than being latecomers to a galaxy already shaped by older, more advanced civilizations, humanity might be among the pioneers, among the first sparks of awareness in a universe that still has trillions of years of stellar activity ahead of it. If that's true, then the responsibility resting on us becomes even heavier and even more remarkable. We wouldn't simply be searching for others who came before us. We might be laying the groundwork for what comes after, for whoever or whatever follows in the billions of years still to come. The truth is that scientists don't yet know which explanation for the Fermi paradox is correct. It's entirely possible that several of these explanations are simultaneously true, working together rather than competing against each other. Simple life might indeed be common, exactly as the chemistry suggests it should be, quietly existing on countless worlds throughout the galaxy, in subsurface oceans, in extreme environments, in places we haven't even thought to look yet. But the leap to complex, intelligent life might be exceptionally rare. It requires a long, unbroken chain of stability, a suitable star, a well-placed orbit, a stabilizing moon, active plate tectonics, a protective magnetic field, and billions of years without a civilization ending catastrophe. And even when intelligence does emerge, the window during which a civilization is both capable of reaching across interstellar distances and stable enough to keep doing so might be tragically brief, a few hundred years out of a civilization's much longer history, easily missed by any other civilization listening at a slightly different moment in time. None of this means we should stop looking. There's a subtle logical trap worth being aware of throughout this entire discussion, something philosophers and scientists call observation selection effects. Simply put, we can only be having this conversation at all because conditions on Earth happen to align well enough to produce a species capable of asking the question in the first place. Any civilization capable of wondering why the universe seems empty must, by definition, exist on a planet where the great filter, whatever and wherever it is, was successfully passed. This means our own existence tells us almost nothing about how common or rare that success actually is across the wider universe. Since we could never observe ourselves from a universe where we failed to appear. It's a bit like a survivor of a plane crash trying to estimate how safe air travel is, in general, based entirely on the fact that they personally survived, without any way of directly observing all the other flights that never make headlines because nothing went wrong, or the rare ones that never landed at all. Our own success in reaching this point offers reassurance about exactly one thing, that the specific combination of circumstances leading to intelligent, technological life is possible. It offers no reliable guidance at all about how often that combination actually occurs elsewhere. If anything, the sheer difficulty of the search is exactly why it matters so much. Every new telescope, every new mission, every new survey of the sky expands the tiny glass of water Jill Tarter once described, bringing us slowly closer to a definitive answer, one way or another. The search for biosignatures has already produced at least one important lesson in caution. In 2020, a team of researchers announced the detection of phosphine gas in the upper atmosphere of Venus, a molecule that, on Earth, is produced almost exclusively by biological processes or industrial activity, since it breaks down quickly and shouldn't persist without a constant source replenishing it. The announcement generated enormous excitement, given that Venus's cloud layers, unlike its scorching surface, sit at a more moderate temperature and pressure, leading some scientists to speculate for decades about the possibility of microbial life surviving in that narrow, floating band of the atmosphere. Follow-up studies, however, produced conflicting results. Some research teams were unable to replicate the original detection at all, while others suggested the signal might be explained by ordinary volcanic activity or unusual atmospheric chemistry unique to Venus, rather than biology. The debate remains unresolved even now, with some researchers still defending the original finding and others remaining skeptical. And it stands as a useful reminder of just how difficult it is to confirm a genuine biosignature from a distance of tens of millions of miles, using nothing more than the faint chemical fingerprint left behind in starlight passing through a planet's atmosphere. Every potential biosignature discovered so far, whether the dimethyl sulfide detected on K218b or the phosphine detected on Venus, requires the same rigorous process. That means repeated observation, independent verification, and careful consideration of every possible non-biological explanation before scientists are willing to call it evidence of life. That caution isn't a weakness in the search. It's the entire point of doing science carefully, especially when the stakes of getting the answer wrong in either direction are this significant. And there's something worth sitting with in all of this, regardless of which explanation eventually turns out to be correct. If we are, for now, alone, the last representatives of consciousness for possibly enormous stretches of space in every direction, then everything we do carries a weight most people rarely stop to consider. Every ecosystem we protect, every discovery we make, every piece of knowledge we preserve and pass forward might be one of the only instances of that knowledge existing anywhere in the observable universe. And if we're not alone, if somewhere out there, on a planet orbiting a star we haven't even catalogued yet, another form of life is asking the exact same question we're asking tonight, staring up at their own night sky in quiet curiosity, wondering if they're the only ones. Then, The discovery that finally breaks this silence, whenever and however it happens, will be the most significant moment in the history of our species. Either answer is extraordinary. A universe with only one form of intelligent life, fragile and rare, beyond imagining, carrying the entire weight of cosmic consciousness on its own. Or a universe filled with countless minds scattered across billions of galaxies, each one looking up at their own stars, wondering the same thing we wonder. We don't know which one is true yet. Both possibilities carry real weight for how we choose to live. A universe where we are alone asks us to treat Earth's fragile, improbable web of life as something closer to irreplaceable, a single, the precious outcome of billions of years of chemistry and chance that will not simply repeat itself somewhere else if we fail to protect it. A universe filled with other minds asks something different of us, a kind of humility. It's a reminder that whatever mistakes, conflicts, or short-sighted choices define this particular moment in human history are not the whole story of what awareness in this universe might become. Somewhere among all those other possible beginnings, other versions of curiosity, wonder, and discovery are almost certainly unfolding in their own way, on their own timeline, entirely unaware of us, just as we remain entirely unaware of them. But for the first time in human history, we finally have the tools to start finding out. Telescopes sensitive enough to read the chemical signatures of distant atmospheres. Radio arrays capable of listening to millions of stars at once. Missions on their way to icy moons that might be hiding oceans of their own. The search continues. One star at a time, one signal at a time, one glass of ocean water at a time. And somewhere out there, whether tonight, next year, or a century from now, that silence might finally break. Good night.